hyperconjugation. So what is hyperconjugation? In this there is a complete transfer of electron of sigma bond towards pi bond. It is also known as sigma pi resonance or no bond resonance, because in this resonance there is no involved or bond. So it is pi resonance positive charge of an electron. So how it is? It is a permanent effect, and how it is being observed? It is observed in three cases. One is alkene or alkyne. B is carbocation, and C is in free radical. In these three cases, we observe the hyperconjugation. So first, let's talk about the alkene and alkyne. A case, alkene and alkyne. So first of all, let's go and look how does alkene and alkyne show hyperconjugation. Let's say we have a CHHH and CH double bond CH2. It is alpha carbon. The carbon next to that alkene is known as alpha carbon, and its hydrogen is known as alpha hydrogen. Alpha carbon and alpha hydrogen. So first of all, this alpha hydrogen should be sp3 hybridized. Alpha hydrogen is not hybridized. Alpha carbon is sp3 hybridized, and it has at least one alpha H. It has at least one alpha H. Then it is in the category to show the hyperconjugation. Now, how does the hyperconjugation occur? So in case of hyperconjugation, we have CH double bond CH2. We have one alpha H. So what will happen? This H plus, this bond will go in this direction. It will become positive, and this bond will shift in this direction. So we have CH double bond CH and CH2 negative, and there is a H plus. There is an H plus, and in that particular case there is no bond, right? There is no bond between carbon and hydrogen over here. This carbon and hydrogen right now don't have any bond, and it is in resonance with this compound. So it will again shift in this direction, and it will form a bond. So hydrogen is not through attached through any bond. So it is called as no bond resonance. So in particular resonance there is no bond involved, or we can say sigma pi resonance. It is sigma bond involved and pi bond involved, and here it is sigma bond involved. So it is also called the sigma pi resonance or no bond resonance. Now there is a one thing to notice, that we have actually this CH2. We have this CH2. We know how many alpha H? We have alpha H has 3. So it will be having 3. It will be having 3 hyperconjugating structure. It will be having 3 hyperconjugating structure. So whenever it has 3 hyperconjugate structure, more the number of hyperconjugating structure, more the stability. So this particular is called as hyperconjugating structure. So more number of alpha H, more will be the hyperconjugating structure, more will be the resonance, more will be the stability of alkene. So here we can identify the stability of alkene also. So first of all, let's talk about some questions where we have to find the number of alpha H. We have to find the number of alpha H. First, I am just writing some questions. So I have drawn all these 11 structures. You have to identify the number of alpha H. So I'm just writing the number of alpha H. Just try to pause the video and try to answer by your own. So it has 12 alpha H. 1, 2, 3, 4, 5, 6, 7, 8, 9, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Here it is 1, 2, 3, 4, 5, 6, 6 alpha H. Here we have 8 alpha H. Here we have 6 alpha H. 1, 2, 3, 4, 5, 6. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 alpha H. Here we have 1, 2, 3, 4, 5, 6 alpha H. Here we have 1, 2, 3, 4, 5, 6 alpha H. 1, 2, 3, 4 alpha H. Here we have 1, 2, 2 alpha H. Here we have 0 alpha H. And here we have 5 alpha H because 1, 2, 3, 4, 5. Here we have 1, 2, 2 alpha H. So that's how we have the total number of alpha H. Now, how do we identify the stability of alkene? How do we compare the stability of alkene? Stability of alkene, now if we talk about stability of alkene. So alkene is directly proportional to number of alpha H atoms. How many number of alpha H atoms? That is the stability of alkene proportionality. Because the number of alpha H is more, the number of hyperconjugating instruction more resonance, more stability. CH2 C, then we have H, CH double bond CH2. It will form CH2 double bond CH, CH2 negative and H positive. But if we have a resonance over here, when we have a resonance, so which alkene is more stable? We know that so first of all we see inductive, then hyperconjugation, then resonance. These are the order we have to remember. If the stability is by resonance, we will be considering it first, then hyperconjugation, then inductive. Remember, we will be solving the questions on this concept later also, but from now just start memorizing that. First of all, we have R, H, then I. So I am just putting some questions. You have to compare the stability. Now there are right now two questions, and in next page I'll put more questions. But right now just try to answer. So let's talk about here. We have 1, 2, 3, 4, 5, 6, 7, 12 alpha H, 1, 2, 3, 4, 9 alpha H, 1, 2, 3, 4, 6 alpha H, 3 alpha H. So this is the order of stability. Here we have 1, 2, 3, 4, 5, 6, 7, 8 alpha H. Here we have 1, 2, 3, 3 alpha H. And here we have 1, 2, 3, 4, 6 alpha H. Here we have 2 alpha H. So this is more stable. Now let's solve some more problems. Now these are all the problems. Just try to pause the video and answer by your own. Now just look at the stability order. If you look at the stability order, in first case, this is more stable because 1, 2, 3, 4, 5, 6, 7 alpha H. Here we have only one alpha H. Here it is aromatic. Here it is resonance, and here it is alpha H. And here we have 6 alpha H. And here we have 2 alpha H. And 1, 3, 2. And here we have this, and this is more stable. Then alkane is stable. Then here alpha H is 10. Here more alpha H. Now if we talk about here, we know 1, 2, 3, 4, it has 6 alpha H. Here we have 4 alpha, 6 alpha H. 6 alpha H. So which is more stable? Let's compare between 1, 2 and 3. As we know that in case of 1, 2 and 3, the most stable will be, whenever we talk about the stability. So in case of stability, this particularly have two groups opposite and these are two groups closer. So there is a repulsion between them. So if we draw their hyperconjugating structure, so simply between A, B and C, B is more stable than C. But how do we compare it with A? So when A has hyperconjugation CH2, H, C double bond CH2, CH3. It will form CH2 double bond C, CH2 negative, CH3. Here we have H plus. Now here we have CH2, H, C triple bond C, H, H, H. Whenever it has resonance, H plus, CH2 double bond C, CH negative, CH3 and H. So which carbon ion is stable? Then this is carbon ion of A and this is carbon ion of B. So in hyperconjugation, we know carbon ion of A is more stable than B. So stability of A will be more than B and C. So these were all about the stabilities of carbon anion in that particular case. But overall, we have seen the stability of alkane. So how do we compare the stability of alkane? Through the hyperconjugation. But if resonance is happening, we will give it to priority. So resonance one is more stable, right? Now let's talk about the carbon ion. Carbocation right now, carbocation. So in carbocation we have similar case. We have CH2H and we have CH positive. So whenever it is going in resonance, H plus CH2, CHH. It is again sigma pi resonance and no bond resonance. Sigma pi resonance and no bond resonance. Now CH3, C plus CH3, CH plus CH3, CH3, CH2 plus, CH3 plus. 1, 2, 3, 4. The stability order will be 1 greater than 2 greater than 3 greater than 4 because alpha H, here alpha H we have 9, here alpha H we have 6, here alpha H we have 3 and here alpha H is 0. So methyl carbocation is the least stable carbocation we ever know, and if we can say it doesn't exist even. So it doesn't exist. So stability of carbocation is directly proportional to number of alpha H atoms, number of alpha hydrogen atom. So here we have 9 alpha hydrogen. We have already written that all the details. Now let's try to solve some problems. Stability of carbocation. So in order to stability of carbocation, we know that we have seen the stability of carbocation through the inductive and resonance also. Right now we are looking, we give the priority of inductive lesser than the hyperconjugation, but the hyperconjugation is less prior than resonance as well. Now let's talk about the stability of carbocation. Now here we have stability. It is 3 degree 9 1 2 3 4 5 6 7 8 alpha. Here 1 2 3 alpha. Here 1 alpha. So these are the order of stability. Now here we have 1 2 3 4 5 6 7 alpha. Here we have 1 2 3 4 5 alpha. Now here alpha is more. Here if you see the inductive effect, the answer will be reversed in third case. But we know as the priority order is R H I. So hyperconjugation will be given more prior than inductive. Here we have second we have resonance, first we don't have. First we have resonance, second we don't have. When both the case we have the same alpha. Here alpha is 2, here alpha is also 2. But if we alpha is same, then we will going to the inductive effect. So when we are going to the inductive effect, so order the stability of the second will become more. Here it is anti-aromatic, here it is aromatic, so more stable. And here it is going in carbocation is going in resonance, and here we have only hyperconjugating effect. Here alpha is 1 2 3 4 4 alpha is here 1 2 3 alpha is. So the order of stability will be more there. 1 2 3 4 5 6 7 alpha is 1 alpha is. So if we write the order of stability, 1 then 2 then 3. So that's how we have seen the stability of carb and ion as carbocation as well. Now let's look out the third stability order, that is for free radicals. Stability of free radicals. Stability of free radicals, C free radical CH3, CH3, CH3. CH2, H, C free radical CH3, CH3. So when it is going in resonance, it will free radical over here, free radical over here, H free radical CH2 double bond C, CH3, CH3. So here also no bond resonance, sigma pi resonance, and here we have alpha H as 9. So these are the alpha carbon. These three are the alpha carbon next to the free radical, and the hydrogen attached to the alpha carbon is alpha hydrogen. So again, stability is directly proportional to number of alpha hydrogen. Like if we solve the questions, this one CH3 one. So this is the order of stability. Second question, this one and this one, this is the order, this will be the order of stability. Now if we divide the hyperconjugation, we could see that there are two hyperconjugation. Hyperconjugation similar, the inductive was plus I minus I, resonance or mesomeric was plus M minus M, and hyperconjugation is of two types, plus H and minus H. Plus H is known as electron donating effect. Minus H is known as electron withdrawing effect. Electron donating effect and electron withdrawing effect. So when we talk about the plus H effect, plus H effect is C, H, H, then H. So when this hydrogen gives its electron pair to over here, so it will form the resonance H plus and C, H, H double bond, and here will be a negative charge, and it will form a negative charge over here also, double bond C, H, H, and here we have H plus. So it could donate the negative charge by 3 hydrogen. So here alpha H are 3. We have donated by 3 hydrogen, alpha H by 3. So this is known as the resonance, the no bond resonance or sigma pi resonance. Right now, what is the difference here? The CH3 group is donating the electron pair to the benzene ring. So it is showing plus H effect. So whenever a group is donating electron through it to the outside, it is known as plus H effect. Now next is CH3, CH, and we have C. So we know first we have alpha H is 3 alpha H, 2 alpha H, 1 alpha H. So stability of the order will be like the electron density in the benzene ring. If we talk about electron density in phenyl ring, benzene ring or phi is known as phenyl ring. So here we have 3 alpha H which are donating more electron to the ring. Here we have 2 alpha H and here we have 1 alpha H. Now if we have CH3, CD3 and CT3 as well. Now let's talk about the second question. We have CH3, we have CD3, we have CT3. So CH3, CD3, CT3. We know the bond length. If we talk about bond length, we have more bond in case of CH, HH. Then we have CD. Then we have CT. We have 3 types of bond length: CH, CD, and CT. So in case of CH, the bond length is more and bond strength is weaker. So CH will break and CD3 then CT3. So CH will break easily. So it will easily increase the electron density in the ring. Again, these are questions related to electron density in the benzene ring. So CH3, CD3, and CT3, the electron density is more in case of CH3. Because CH bond is weak, it could easily break and it will give easily hyperconjugating structures more. So we calculate if we compare the electron density in the benzene ring through the some questions other, like if here we have CH3, here we have CD3, here we have CT3. So CH3, CD3, CD3. Now there is no alpha, there is no hyperconjugation because this double bond is not, the alpha carbon is not having hydrogen. So here we can only have plus I effect. Here we have plus I effect only working. So CT3 has more plus I. So the benzene ring electron density order is this. Now if we have one more question regarding plus H. So we have CH3 and we have OCH3. So OCH3 is resonance effect. It will give the resonance. It has plus M effect and it has plus H effect. So order will be through the plus M will be more. Plus M will increase more electron density in the benzene ring as compared to the second. So this was all about plus H. Now we talk about the minus H. Reverse hyperconjugation, or we can say minus H effect. Minus H effect, or sometimes it is known as reverse hyperconjugation. So we have CF3, CCl3, CBr3, CI3. So in case of CF3 there is no reverse. Remember, in case of CCl3, only CCl3 show reverse hyperconjugation. Now how does it show? Cl, we know CF bond is strong, bond is more strong. In case of CF, bond is more strong. In case of CBr, there is more overlapping difference between carbon and bromine. And CI3, there is more stronger bond distance, overlapping distance between carbon and iodine orbital. Now CCl3 we have. So in case of CCl3, electron will be pulled towards this. It will form a positive charge, Cl, and it will be Cl negative. Now it will show the resonance over here. And Cl negative. So it will show the resonance like this. This is also known as reverse hyperconjugation. So it's actually withdrawing effect, decreasing electron density in benzene ring. So it is negative H. So it is actually pulling the electron towards it. So it is minus H. So that's how we have defined. Now why CCl3 only? Let's write what we have told again. CCl3 show minus H. But CF3 bond energy is high, very high. But in case of CBr3, in case of CI3, you can say overlapping difference is more, or you can say no difference of electronegative. So it will not lose as a I negative, it will not lose as Br negative, because electronegative difference is more. So now let's solve some electron density question through the overall effects. First we have CCl3, then we have CH3, then we have NO2, then we have OCH3. So this is minus M, this is minus H, this is plus H, this is minus M, this is plus M. So electron density increases by first, then we have plus H second, then we have third minus H, then we have fourth. Mesomeric effect is more than hyperconjugation because there is a pi bond cleavage, but here the sigma bond breaks. So more easily is to break the pi bond, so more effective is the mesomeric effect. And in case of hyperconjugation and mesomeric, we already know inductive and hyperconjugation. The inductive is the not the complete transfer of electron, but in case of hyperconjugation, there is a complete transfer of electron. Now second case, if we talk about, we have a case of CCl3, CCl3 and CCl3, and here we have CCl3, CCl3 and CCl3. So here we have minus I effect rather than here we have minus H effect. So the answer will be like this. Minus H will, the electron density will be more in case of first one, because second minus I has more less electron density as compared to first has more electron density because it has less powerful withdrawing group. Instead the second one has more powerful withdrawing group.